Section 5.3, matrix equations. Okay, and this sort of ties into the previous section where we converted a system of linear equations into an augmented matrix. However, even though this section is leading up to an alternate way to solve systems of linear equations, we're gonna go about it in a different fashion. Okay, and first, what we need to do is learn a little about what's called the identity matrix. Okay, um, if you took intro algebra, I'm not sure if this really comes up specifically in intermediate, but you should remember the identity element of particular numbers. So, for instance, if I were to write 2 times 1, with 1 being the multiplicative identity element, then we would simply get the 2 back. 2 times the identity element gives us a 2. Alright, so if I take 1 and multiply it by any other number, I can take a half and multiply it by 1, then I'm simply going to get that number back, 1/2. Okay, and that applies to negative numbers, positive numbers, zero, fractions, irrational numbers, any real number that you can think of. If we multiply it by 1, we get the same number back. So let's see, negative 3.56 times 1 gives us negative 3.56. And so matrices have a similar identity matrix, where if you take a matrix and you multiply it by the identity matrix, you simply get the original matrix back, the one that you started with. So for a 4 by 4 matrix, if we multiply it by this matrix listed here, and it's labeled I for identity, we'd get the matrix back. So down here you see that we have this matrix A. For any square matrix A, if we multiply by I, the identity matrix with the same dimensions as A, we can multiply it on the left or the right. We simply get A back. Here, the third matrix is the identity matrix for a 3 by 3, and the last one is the identity matrix for a 2 by 2. Okay, so the identity matrix has the same dimensions as the matrix that you're multiplying it by, and then you simply get that matrix back. Okay, so in example 1, what they want us to do is take A and B and multiply it by their identities. Okay, so A is a 2 by 2. So the identity matrix for A will be a 2 by 2, where we list only ones in the principal diagonal, and then all of the other elements are 0. The identity element for B matrix will be a 3 by 3, because B is a 3 by 3 with ones in the diagonal and zeros elsewhere. Okay, what they want us to do is to confirm that I times A equals A, and likewise A times I equals A. Okay, just like for instance, if I took a real number, not a matrix but a real number, and I multiplied 1 by 2, for instance, and then 2 times 1, the identity element multiplied from the right, either way you get 2. Okay, it just simply gives us the number that we multiply by 1 back. Alright, except we want to use matrices instead of real numbers. So we'll go about checking this this first one. We have 1 1 0 0. Okay, and this is I times A. What do we actually get? Well, A is a negative 2 1 3 0. And now what we do is we multiply the rows by the columns of A. The rows of I times the columns of A. So the first row and the first column will give us this first element in A. The first row times the second column will give us this entry in the product, and then so on and so forth. Second column, first row gives us the, the second row, first column gives us the second row, first column of the product. Okay, so in other words, we have 1 0 1 first row times the first column gives us 1 times negative 2 plus 0 times 3. And you can see that the 0 knocks the 3 out, and we just simply get a negative 2 there. Okay, and it matches up with A exactly. Now if we take the first row times the second column, we have 1 times negative 2 plus 0 times 1 from A. The 0 knocks out the 1 as it did with the 3, and we get, oh, I'm sorry, I put the wrong number in here. The 1 should have multiplied this 1, and then the 0 should have multiplied the 0. I guess I'm still trying to do the first one. 0 times 0. Okay, so we get 1. Next, we take the second row of I and multiply it by the first column of A. 0 times negative 2 and plus 1 times 3. 0 knocks out the negative 2, 1 times 3 gives us 3, and so far all of the elements of the product match A. Okay. Second row, first column is 3. Second row, first column is 3 of A. And finally, our last element of the product, 0 1 times 1 0. So we get 0, this 0 times 1 plus this 1 times that 0, and it works out to be 0, which matches A also, and so this product, this matrix, must equal A. So I times A equals A. Alright, what if we do it in the reverse order? Will we still get A like we're supposed to? Alright, we'll go back and we will write A times I. So we've checked this first one off our list, and now we want to write A times I. What does that equal? Okay, well, I, the identity matrix, is easy. 1's in the principal diagonal, 0's elsewhere. A is negative 2, 1, 3, 0. Alright, so when you multiply matrices, you take the rows of the first matrix times the columns of the second one. Negative 2 times 1 plus 1 times 0. Well, the 0 knocks out this 1, and we get negative 2, which matches A. Okay, what about the second element of row 1? We have first row times the second column. So negative 2 times 0, and then plus 1 times 1. 0 knocks out the negative 2, and 1 times 1 is 1, which matches A. Okay. Second row, first column, we have 3 times 1 plus 0 times 0. The product of the zeros doesn't contribute, and so we have 3 times 1, 3, which matches A. And finally, the second row times the second column, we have 3 times 0, this 3 times the 0, plus 0 times this 1. Everything cancels out. This 0 knocks out the 3, that 0 knocks out the 1, and our sum works out to be 0 for second column, second row. So this matrix here matches A completely. And so this little matrix equation checks out too. Okay, and now we want to do the same thing with B. Okay, what I'll do is I'll bring out my calculator, and we'll use the matrix capabilities to do this for us. What we want to do is check and see that identity matrix for 3 by 3 matrix, 3 by 3, one's in the principal diagonal, zeros elsewhere, times B equals B. And then we also want to reverse the order, B times I, and verify that that equals B as well. So to do that with our calculator, we go to second matrix. We will edit B, which is a 3 by 3. Enter the elements, 1, negative 3, negative 6. Four, negative 3, 2, 5, 8, and 1. Okay, so B is in our calculator. We go back to the matrix screen, and we'll see if we can get I. Okay, there is an I matrix, so we go to edit, we scroll down to I, and in the calculator I isn't automatically the identity matrix. We have to enter the ones for the principal diagonal. And we can arrow around to avoid having to enter 0 so many times. And so we take the principal diagonal, we put in ones, zeros are already in the other spots, and we hit enter, and we go back to the home screen. And now we want to verify I times B equals B. So if we go to second matrix, we select I first, it's going to hit enter under the names menu, and it's going to take I back to the home screen. And now we want to put matrix B beside it to the right, and so we have I times B. That equals this matrix, which is identical to B. 1, negative 3, negative 6, 4, negative 3, 2, 5, 8, 1. And so we've just verified that I times B does in fact equal B. What about the reverse order? All we have to do is go to the matrix screen, select B first, back to the matrix screen, select I second, hit enter, and again we get B. 1, -3, -6, 4, -3, 2, and 5, 8, 1. And so we verified the second matrix equation, B times identity equals B. Okay, definition 2 defines the inverse matrix of a particular matrix. Each matrix has its own inverse. Every matrix has, for instance, well, depending on the dimensions, every matrix pretty much has the same identity matrix. So for all 2 by 2 matrices, the identity matrix is for all 2 by 2 matrices. The matrix 1, 0, 0, 1 is the identity. Okay, but in this case, we're sort of rephrasing the problem. We're not multiplying something by the identity. We're multiplying 2 matrices together and we're calculating the identity matrix. We're actually getting the identity matrix as a result. Alright, and so let's sort of put that in terms of real numbers. So for instance, if I take 3 and I multiply it by some other number, and what I want to do is get the identity element of real numbers, which is 1. So what do I multiply by 3 to get 1? Well, 1/3. And so we say 3 and 1/3 are inverses of one another, because when we multiply them, we get 1, the identity element. However, if I pick a different number, let's say if I pick the real number 3/4, well, what do I multiply by 3/4 to get 1? Well, with the real numbers, it's pretty simple. I just flip this fraction here, 4/3, and I keep the same sign. 3/4 times 4/3 equals 1. So 3/4 and 4/3 are inverses of one another. Okay. Now mathematically, there is a procedure that we can use to find the inverse of a matrix by hand on paper. But what we're going to do in this chapter is just simply use our calculator to do this. Alright. And as the definition states, an inverse matrix is not guaranteed to exist. Notice the underlined phrase here, if it exists. Okay, so example 2. We're given matrix A. Here are the elements of matrix A. And what we want to do at this point, this isn't like real numbers. Finding the inverse of a matrix is more difficult. We can't just simply flip the matrix or anything like that. So we want to rely solely on our calculator. We go to the matrix screen, and our matrix is called A, so I would just stick with that. The edit screen, we enter 3 by 3. And now we enter the elements 1, -1, 1, 0, 2, -1, 2, 3, and 0. Okay. We'll hit second quit, go back to the main screen. Okay, so we're going to rely solely on our calculator to find the inverse matrix in this section. So let's talk about the numbers. Let's look at real numbers first. First example that I showed with the real numbers was 3 times 1/3 equals 1. Okay, and so 3 and 1/3 are inverses of each other. So what did we do with the 3 to find the inverse? Well, we simply looked at the 3 as a fraction, 3 over 1, and we flipped the fraction. Well, it turns out there's actually something that we can do mathematical other than to just simply say flip the fraction. So, for instance, we said 3 over 4 times what equals 1. Well, we said flip the fraction, take the reciprocal, which is 4 over 3. Well, it turns out what we can actually do for the inverse, and these look like matrix brackets, but they're not. I'm just using them as grouping symbols. So if we didn't know about flipping the fraction to get the inverse, what we could do mathematically is to say the inverse of 3/4 is simply 3/4 raised to the -1 power. And for real numbers that works. That gives us the inverse. And so if we multiply these two numbers together, 3/4 and 3/4 to the -1 power, we get 1. Okay. And if you remember the product rule, when you multiply two things with the same base with different exponents, you can add the exponent. So another way to look at this would be 3/4 to the first power times 3/4 to the -1 power would give us 3/4 to the 1, and add the exponents minus 1 is 3/4 to the 0 power. Well, 3/4 or anything raised to the 0 power, any real number raised to the 0 power, simply gives us a 1, which is what we want because we want the two numbers to be inverses of each other. So this trick with the -1 and the exponent works for real numbers, and you can actually verify that with your calculator. If you take 3/4, put it in parentheses, and raise it to the -1, we get 1.3333. Well, what is this in fraction form? It's 4/3. Okay, so I say all of that just sort of make sense of what we're going to do to actually find our inverse matrix. We're going to take the matrix that we want to find the inverse of and simply raise it to the power of -1. Okay, there isn't actually a operation in the matrix math menu. Okay, if you go to math and you scroll down through the list, there is no inverse matrix operation. Okay, we do want to enter matrix A into the calculator, and here we have it. All right, you can double check it. Just simply go back to edit A, 1 -1 1 0 2 -1 2 3 0. Okay, return to the main screen. There is our matrix A. So now we just simply want to raise it to the -1 power and hit enter, and there we go. Here is A inverse. So now if we write that out, and I'll use the matrix brackets, A inverse, we have 3, 3, -1, -2, -2, 1, -4, -5, and 2. So if you compare the two matrices, there's really no short and simple way to arrive at the inverse matrix. Okay, we're not just simply taking the reciprocals of the number or anything like that. It's a bit more complicated, and so for the sake of this class, we're just going to use our calculators. It's good for you, right? Okay, well, we're not finished. The workbook, example 2, wants us to verify that A times A inverse equals the identity matrix. So we're not trying to multiply two matrices and get one. We're trying to get the identity matrix. And so in other words, we're dealing with a 3 by 3. What we want to get when we multiply this matrix and the one that I found with the calculator is this 3 by 3 with the ones in the principal diagonal. Okay, this is the identity matrix, and that's what we're going to get when we multiply these two. Okay, so I guess I could do this by hand. It's quite a bit of work, but what I'll do is I'll sort of scribble this out, and this is A. What happens if I multiply it by A inverse? I will put it right beside A that's already written in the workbook. And we start off with the rows of A and multiply them by the columns of A inverse. Okay, so row 1 times column 1. 1 times 3 plus negative 1 times negative 2 plus 1 times negative 4. 1 times negative 4 is negative 4. Okay, well this is 3, and then plus 2 is 5, and minus 4, we get 1. Alright, and I do this because more than likely I'm going to run out of room here. There's not enough space to actually work this out by hand, but I'll do a couple of them just so that you get the idea. Okay, and then we can just verify with our calculator. So first row times first column. Now we want this element here. Okay, first row, second column. So we take the first row and multiply it by the second column of A inverse. We get 1 times 3, 3, negative 1 times negative 2, positive 2, and then 1 times negative 5 minus 5. Well, 3 plus 2 is 5 minus 5, we get 0. So maybe if I don't write it out completely, I'll have enough room to do the rest of it. So now we do the first row times the third column, and it goes in the first row and the third column, right here in the product. 1 times negative 1 minus 1, negative 1 times 1 minus 1, 1 times 2, that is a 2, isn't it? Yeah, it's a sloppy 2. Okay, 1 times 2 plus 2. Well, turns out to be 0, which is exactly what we want. We want the identity matrix here. 0 times 3 is 0, so now we're doing the second row in the first column, so we're going to end up in the second row in the first column here. Okay, it goes right there. 0 times negative 2 is 0, or I'm sorry, 0 times 3 is 0, 2 times negative 2 is a minus 4, negative 1 times negative 4 is a plus 4, negative 4 and 4, 0. Second row, second column, 0 times 3, 0, 2 times negative 2, minus 4, and negative 1 times negative 5 is a plus 5. Negative 4 plus 5, we get the 1 in the principal diagonal. Okay, second row, third column. It's going to go right there and right here. We're expecting to get a 0 here. Alright, so let's see if that actually works out. 0 times negative 1 is 0. 2 times 1 is plus 2. Negative 1 times 2 is a negative 2. 2 minus 2 is 0. So that checks out. And our last row, so we have 3 more elements to calculate. Alright, third row, first column. Goes in the third row in the first column. 2 times 3, 6. 3 times negative 2, minus 6, and 0 times a negative 4, 0. 6 minus 6, 0. 2 times 3, 6. 3 times negative 2, minus 6, and then 0 times negative 5. 0. 6 minus 6, 0. Alright, so none of these first two elements of the third row, neither one of them are in the principal diagonal, so they should be 0. Now, third row times the third column gives us third row, third column of the product. 2 times negative 2, or I'm sorry, 2 times negative 1 is negative 2. 3 times 1 plus 3, 0 times 2, 0, negative 2 plus 3, 1. Alright, so we checked this out by hand, and it really wasn't too bad as long as you do some of the math in your head. Okay, but A times A inverse does result in the identity matrix. Alright, and as I promised, we will use our calculator to do the next one. What is A inverse times A? Is it the identity matrix? Alright, so pull up the calculator. We already have, let's see, we already have A up here in the calculator somewhere, maybe not. Okay, well, there is A inverse. So what we want to do is bring this one down. Let's see. There we go. A inverse comes first, like I wrote here. And now we want to go back to the matrix screen and enter A and bring it to the home screen. So A inverse times A, enter. And there we go. There's a 3 by 3 identity matrix with ones, only ones in the principal diagonal and zeros elsewhere. So this does check out. Both of them checked out. We did the first one by hand, this one with the calculator, and we did this one by hand, and they both checked out. And that's all the example wanted us to do. Okay, well, how do we actually use this to solve the systems of equations, the ones that we saw from the previous section? Well, we no longer write this as an augmented matrix, where we include the coefficients and the constants d in the same matrix. Okay, what we do is we split them up into separate matrices. Okay, we're going to have an A matrix where we only list the coefficients. We're going to have a variable matrix where we only list the variables x, y, and z. And then we're going to have the right hand side of our matrix equation D, okay, where we list the constants, or what we're supposed to get from the three equations. Okay, D1, D2, D3. Alright. If we look at the next page, it gives us a better idea as to why this works and what exactly we're going to do. Now you'll see here that this is the equation. Okay, we can take a system of three linear equations with three unknowns, split it up into coefficients A, variables x, and constants d. And then to solve the equation, what we do is we take both the left and the right hand side of the equation and multiply it by this inverse matrix of A, the inverse coefficient matrix. What happens, okay, here we've inserted the inverse matrix to the left of A. Well, what happens is the A inverse cancels out the A that's there, and we're simply left with identity matrix times x. Okay, but just like all the other equations that we've solved in algebra, what you do to one side you have to do to the other. So you see another inverse matrix listed on the right, okay, in front of the D. And so what we have on the left is I times x, which turns out to be simply an x because I is the identity matrix. Okay, I times this matrix x is x. and then our answer lies in multiplying a inverse times D. Okay, so this is what we're looking for. This is what we're going to get compute in our calculator. If you compare this to real numbers, say for instance, let's take the equation 2 y equals 4. Okay, we're not talking about matrices. These are just real numbers and a single variable. Well, usually what we write to solve this equation is we divide both sides by 2. And we get y equals 2. Well, there's another way to look at it that falls in line with this method that's laid out here for matrices. What we do is we say, well, I want the y by itself. Okay, here's our solution, y equals 2. The y is completely by itself. In other words, there is a 1 coefficient sitting in front of this y. Well, how can we take a 2 that's sitting in front of the y with the original equation? How can I take a 2 and turn it into a 1? Well, we just take the 2 and multiply by its inverse, 1 over 2. We multiply by half, and so that's the same thing as up here when I divided both sides of the equation by 2. Just sort of looking at it in a different way that aligns with this method over here to the left. So to get a 1 in front of the variable, we multiply by the inverse 1/2. What we do to one side, we have to do to the other. So I place a 1/2 in front of the 4 on the right. 1/2 times 2 gives me 1y. 1/2 times 4 gives me 2. A 1y is the same thing as a y. Okay, it doesn't change it. It's sort of analogous to this identity matrix times x. It's just equal to the x. So we have our variable by itself, y, and we have our answer here that's easily computed with real numbers. 1/2 times 4 is 2. But in the case of the matrices, we're going to have to multiply this in our calculator. We can't just do this in our heads. So the answer is easier to get when you're dealing with a single equation and real number coefficients. A little difficult with matrices, but the method is pretty much the same. Okay, we're just going to multiply the right hand side of our matrix equation by the inverse of the coefficient matrix. Alright, so how do we write this system of equations? We've got 2 equations and 2 variables, x and y. How do we convert that to a matrix equation? Well, I am going to write matrix C for coefficient matrix times x, our variable matrix, and that equals D, our constant matrix. Okay, D is just going to consist of 26 and -7. Alright. C is 4, 3, 3, -11. The variable matrix, x, I didn't put the y, but that matrix is x, y. We only have variables x and y in our equations. This is a system of 2 equations, so 2 variables. And then D is the matrix, column matrix, 26, -7. Alright, well, to solve this, we take the left hand side, multiply by the inverse matrix C, and then we scoot over the right hand side and do the same. Multiply the right by C inverse. And another thing that's different about matrix equations is that we want to make sure that we use the same order on the left and the right side. Okay, matrices are not commutative in most cases, so make sure you put the inverse matrix, coefficient matrix, on the left side of the constant matrix, the D matrix. Okay, well, This is our answer. This is all we want to do with our calculator. We want to put C in the calculator. We want to take C inverse and multiply it by this matrix D, 26 over negative 7. Alright, so let's walk through that with our calculator. Okay, we'll clear everything out. We'll go to the matrix screen, and we're going to use C and D. We don't have to put the variable matrix in our calculator. That is unnecessary. C, we scroll over to the edit screen and we select C. C is a 2 by 2. Okay, this is C. We're not entering in C inverse. We have to calculate C inverse. We want to put these numbers into C. 4, 3, 3, negative 11. So 4, 3, 3, negative 11. Enter. And we're done with that one. So we go back to matrix, or I suggest going back to the home screen and then going back to the matrix menu. Okay, and we have one more matrix to enter. I don't want to bring it to the home screen. There is no matrix for D, so just a mistake there. Let's go back and actually enter in D in the edit screen. D is a 2-row 1. Okay, didn't mean to put 21 there. Okay, clear that. 2 by 1. And the elements are 26 and negative 7. Alright. Simply go to the home screen and we compute this. This stuff in the red box. C inverse, or C raised to the negative 1. Okay, except this negative 1 isn't interpreted as an exponent like we usually interpret it with real numbers. This negative 1 just indicates that we want the inverse. It's just communicating to the calculator that we want the inverse of C. So we bring C to the home screen. We enter in the exponent of negative 1 to get the inverse. And then we arrow over and we go back to our matrix screen and select D to put it in front of C inverse, and we hit enter. And there we go. 5, 2. This equals the matrix 5, 2. In other words, what this translates to is x equals 5 and y equals 2. Does it actually work? 2 by 2 matrix, or 2 by 2 system of linear equations. Pretty quick to check it out. We want to put in 5 for x, 2 for y. Well, 5 times 4 is 20, plus 3 times 2, 6, does give us 26. So the first one checks out. We check the second one and it checks out, then the matrix 5, 2 must be a solution. Alright, 3 times x, which is 5, minus 11 times 2. Does that equal negative 7? Well, we have 15 here, minus 22. And the difference between 15 and 22 is 7, and it's negative because the 22 is bigger, so that one checks out. So this is the solution to the system. Okay, so real simple. What we want to do here is we'll call our coefficient matrix. We'll go ahead and write it out. 1, 3, negative 2, 2, negative 1, 1, and 3, 2, negative 3. And our answer already, we're dealing with a 3 by 3, a system of 3 equations. So our variable matrix is going to look like this. And to compute x, y, and z, what we do is we take the c that we wrote out above, calculate the inverse, and then multiply that by the D matrix, which is 8, 1, and 15. So again, the only thing we really need to put into our calculator is this. We need to enter C matrix and D matrix and then calculate this quantity here. I'll use C and D again. I'll have to type over C because now it is a 3 by 3. And our elements are 1, 3, negative 2, 2, negative 1, 1, 3, 2, and negative 3. Alright. We also need a new D matrix with the numbers 8, 1, and 15 arranged in a column. So we want a 3 by 1 matrix. 8, 1, 15. Go back to the home screen and we simply enter in this calculation here. C inverse, matrix screen. We call out C to the home screen. We enter the exponent negative 1 to indicate inverse of C. I didn't need to hit enter, but we can just simply pull C inverse down to the next line. Apparently C inverse is pretty nasty. These digits here, these decimal numbers, don't look like rational numbers. So we definitely need to rely on our calculator for this. C inverse, and then we put out to the right of it matrix D, hit enter, and the numbers turn out to be pretty friendly. 2, 0, negative 3. 2, 0, and negative 3. Okay, so this simply tells us x equals 2, y equals 0, and z equals negative 3. These numbers should work for all 3 of these equations. Alright, so to double check this, we'll check the first one. X is 2 plus 3 times 0 minus 2 times negative 3. Does that equal 8? Well, 0 knocks out the 3 and we get a 2. Minus 2 times 3 is a plus 6. 2 plus 6 is 8. Okay, and this is that's just an equal sign there, it's not a 2. Equals 8. So that checks out. What about the second equation? 2x, so 2 times 2 minus y, which is 0, plus a negative 3. Does that equal 1? Well, we get a 4 minus 3. Yes, that does equal 1. Okay. And finally, to nail down that these are our solutions, you have to check all 3 equations. So 3 times 2 plus 2 times y, which is 0, minus 3 times negative 3. Well, 2 times 3 is 6. 0 knocks out the 2. Negative 3 times negative 3 is plus 9. and that does equal 15. So our solution checks out. All right. And our last example, to convert this, which I probably should have done in the previous one, but what you want to do, if you were given this as a show your work on the test, you want to write out the matrix form of this system of equations, which would be 2, -5, 3, 3, 2, -1, 1, -3, -4. So this is our coefficient matrix. We could write that as C, and then we multiply that by the variable matrix XYZ, and so up here in shorthand we could just write matrix X, and then equals our constants D. So the column matrix -18, -12, -4. And then here we can write D matrix for shorthand. Okay, what's the solution to this matrix equation? What is X? What is X? And now X is a matrix. Okay, X is going to give us a column matrix with 3 rows. It's going to give us our X number, Y number, and Z number. Alright, to compute that, we simply put C inverse to the left of C on the left side of our equation, and then we put C inverse on the left side of D, right side of the equation. Well, C inverse times C gives us the identity matrix times the variable matrix. And this matrix here is going to give us our solutions in the form of a column matrix with 3 rows. Identity matrix times X is just X itself. Okay, so this is what we're doing here. This is all of the steps. Okay, you don't have to, you can just simply use C and D. You don't have to write these numbers out over and over, but I do want you to know what's actually happened. What steps are we taking with this matrix equation to arrive at our solution? And our solution is this. This is what we want to put into our calculator. C inverse times matrix D. So pull our calculator up, go back to our matrix screen, edit C. It's still a 3 by 3, and we have new numbers: 2, -5, 3, 3, 2, -1, 1, -3, and -4. Alright, so we have C, we've got that right here. Now we need to put D into our calculator. So I hit second quit, clear out my calculator because I'm fixing to put some stuff here, fixing to type out this C inverse D. But first I have to go back to my matrix screen, edit, and enter the new D. It's still a 3 by 1, but we have new numbers: -18 for the first row, -12 for the second row, and -4 for the third one. Alright, okay, so there it is. Now we go back to the home screen. Alright, we hit second matrix. Under the names menu now we select C. We put in the inverse notation, exponent -1, arrow over to the right. Okay, don't hit enter because then it'll just calculate it. You have to hit the arrow button over to the right, and then you want to enter matrix D. Enter, and there we go. There's our solutions. We have the matrix -5, 1, -1, which tells us that x is -5, y is 1, and z is -1. So this is the last example. It's a little bit of work, but let's double check our solutions. 2 times -5 minus 5 times 1 plus 3 times -3. -10 minus 5 minus 9 obviously that doesn't equal -18, and so if you double check the numbers for our variables, you would see that z is not -3, it's actually -1. So I guess I just sort of multiplied that in my head real quick, but we get not a -9 but a -3, which is good because this now ends up equaling -18. So I had a scare there for a minute, but equation 1 does check out. Second equation, 3 times -5 plus 2 times 1 minus z, which is minus a minus 1. Okay, this is a -15 plus 2 plus 1. -15 plus 3 equals -12. Equation 2 checks out, and we have one more equation. X is -5 minus 3 times y, which is 1, minus 4 times z, which is -1. Okay, does this add up to give us -4? Minus 5 minus 3 plus 4, minus 5 and a minus 3 is -8, plus 4, we get the -4. So the third equation does check out. And that was our last example. So that completes section 3. Thanks for watching. Enjoy your Thanksgiving.